Okay, there are different types of frames. Frames can come in different shapes. Okay, you can have a symmetrical frame. You can have a geometry symmetrical. You can have the loading symmetrical or bolt symmetrical. You can have a one-bay frame. You can have multi-bay frames, multi-story frames. So there are all sorts of frames that we could potentially do. But obviously, we haven't got the a lot of time to do a lot of frames. So I'm going just to show you a few examples on how to use the moment distribution method for frames. The main thing I would like to mention here is that we are looking only at frames where no sway takes place. Get the sense sway? Yeah, so there is no lateral movement. I mean, if you take a frame like this, for example, I'll just give you an example here. When you for this frame here, when you apply the loading, do you agree that the frame is going to sway like this? Yes? You agree? That's so here we have a sway. This is a sway frame, okay? If I take the same frame and I block the lateral movement, so you agree here that the frame cannot sway. Yeah? Because it's prevented. So there is no lateral movement because it's prevented by the rigid support here. So this is a case of a non-sway frame. The analysis using moment distribution, the analysis of non-sway and sway frames is actually different. Okay, it takes longer to analyze sway frames using moment distribution. Okay, you need to do it in two stages. You need to do it. You need to perform the analysis as if there is no sway, and then you take into account the lateral displacement here into the analysis. So you do it like in two stages. So it takes longer. And for this reason, I'm not covering this here. We are just going to cover non-sway frames. Is that clear? Because they are a lot simpler, and these will take a lot longer to perform. They're not difficult. It just take longer because you do it in two stages. And you need two tables, right? You do it without sway, and then you include the displacement here into the analysis. You can look at it in the textbooks if it does make sense, but it's not part of our syllabus. Okay, so we're just looking at non-sway frames. All right. So I'm going to, in terms of the analysis itself, using the moment distribution method, there is absolutely no difference between frames and continuous beams. So what we did yesterday is still valid, and we can still apply it for frames. So the theory itself, the steps are exactly the same, right? So in that respect, all we are doing here is actually analyzing a structure that has a different shape to a continuous beam, but the actual theory and the steps involved are exactly the same. Is that okay? So let's take an example. Okay, so we take an example, and I've chosen this example here. So we have a frame, ABC. It carries a central load of 100 kilonewton at mid-span. So we have 2 meters and 2 meters, and the height here of the column is 4 meters. given the rigidity of the column is EI and the flexion rigidity of the beam is 2EI. So, how do we analyze this frame using moment distributions? That's the question. So we want to determine, we want to draw the bending moment diagram for this frame using moment distribution. Okay. Now, as I said just a minute ago, the analysis is the same as that for continuous beam. In fact, this frame here will be equivalent as if you had a continuous beam like this. So you substitute this joint beam as if you had a intermediate support here, and you've got this. Can you see that? Yeah. So this is like if you had a continuous beam that looks like this. So in that respect, everything that we're going to do here, as if you had a continuous beam. So you determine the fixed moment, the distribution factors in exactly the same way. So we are dealing with the frame, obviously. It's different to a continuous beam. But what I'm saying is that in terms of analysis, it's equivalent to a continuous beam. But obviously it's a frame. Is that okay? Yeah. So now we're going to start the analysis, and the first step would be we determine the fixed end moments. So the first step is to determine the fixed end moments. So for member AB, what have you got for AB? Is it loaded? No. So fixed moments? There is no load, 0. Yeah. So we have the fixed end moments at A, FEM AB is 0, and FEM BA is also 0 because AB is not loaded. Okay. Similarly, for member BA now, BC. This is member BC. We have got this here. It's 100, and then we have 4 meters. Okay. And the load is in the middle. We have 4 meters, and the load is in the middle. If you look at your table, so it's minus, is it WN over 8? Yeah. You've got your table? Yeah, so we have minus WN over 8, which is minus 100 times 4 over 8, which is 50. So it's minus 50 kilonewton meters. And similarly for CB, it's plus 50 kilonewton meters. Just checking it was recording. Yeah, so it is recording. That's good. Any questions? Is that clear? So that's the first step. Second step, we do now the distribution factors. Okay, now we do the distribution factors. We have got joint A. We've got DFAB. If it's fixed, what is it? What did you say? 0. Yeah. Then for joint B, we have DFBA and we have DFBC. Okay. DFBA, we have 1/4 divided by 1/4 for AB, and then we have 2/4. So I think it's 1/3. And then for BC, stiffness of BC, which is 2EI/4, so it's 2/4, and then it's 1/4 plus 2/4, and this is 2/3. And you can see that the sum is 1. And finally, for joint C, we have only one member at C, and that's DFCB, and it's equal to 0 because the joint is fixed. Any questions? Are the distribution factors clear, please? Yeah. Yeah? Okay, so just using the definition. It's always the stiffness of the member under consideration, so in this case BA, and then you add the stiffnesses of all members connected at the particular joint, like here, joint B. Okay. That's it. So now we've got everything that we need to construct the moment distribution table. If there is anything not clear, please just ask. Okay. Right, so let's do the distribution table. So moment distribution table. Yes.
I just wanted to ask, the way you converted the frame to the other structure, is there a way of determining which one to choose, or is it just an automatic?
No, this is just for illustration. Yeah, it's equivalent to analyze it because you can see here that's the same analysis. Yeah, but a frame is a frame. It's a frame. But what I'm saying this is equivalent. You can think of this as if you had a continuous beam in terms of the analysis. Okay. So we have the joints, we have the members, then we have the distribution factors, and finally we have the fixed end moments. Okay? We have three joints. We have joint A, joint B, and joint C. For joint A, we have only one member connected to A, and that's member AB. For joint B, we have two members connected to B. That's member A, BA, and member BC. And finally, for joint C, we have one member connected to joint C, and that's member CB. Okay, then we write here the distribution factors. For AB, we have 0. For BA, we have a third. For BC, we have 2/3. And for CB, we have distribution factor is 0. Then fixed moments. AB, we have 0. BA, we have 0. BC, we have minus 50. And CB, we have plus 50. And we have an out of balance here. We have an out of balance of minus 50. So the balancing moment is plus 50. Yeah? So the balancing is plus 50 to give you equilibrium. Okay? So therefore, what we do, we take the balancing moment, so we change the sign here. So we have 50 times a third. Okay? We have 50 times a third. What is 50 over 3?
17.
Sorry?
17.
17.333, isn't it? Yeah. So we have plus 17.33 reoccurring. And then if you do 50 times 2/3, please, for me. Is it 23, 67? Sorry? 34. No. 33. Yes, 33.37. 36. Or 37. So when you add them up, you should get the 50 here. Is that okay? Yeah. Now can you see here, we've got. Sorry?
Yeah, I thought so. Should be 16.6. It's supposed to.
You check it. I haven't got a calculator. Do for me 50 divided by 3. Is it 16?
16.6.
Okay, thank you.
17.
Now, you see here, we've got end A fixed. And we've got C also fixed. So because they are fixed, so you need to carry over half from there to there and half from B to A. Is that clear? Because they are fixed. So we carry over half from joint B to joint A, and we carry over half from joint B to joint C. So 1633 divided by 2? 8. 16? Is it 16?
Yes.
And you carry over 33.37 over 2, please.
The numbers should be 16.67 and 30.
Yeah.
I don't know. You haven't got a calculator. I think I should rely on myself. Because everyone is giving me different. Okay, so 50 divided by 3 is 1667 here, isn't it?
Yeah.
And then 33.33 then.
Yeah.
So this is 834. And this is 16. 69? Thank you very much. Okay, so we add them up. So these are now the final moments. So this is balance. This is carry over. Carry over. Okay, and we have the final moments.
When would we have to do balance and carry over more than once?
If you have two members only, like here,
Yes.
it's always one. Yeah, it's only if you have multi-span, yeah. Because here, if you have two members, you only have one joint in the middle to balance. Okay. So add them up. We have 1834. Then we have 1667. And I believe if you do minus 15 plus 33, you should get minus 16.67. And that is 66.69. And we can see that the joint now, joint B, is now in equilibrium, balanced. Okay? Okay, so that's the so these are the results now. We've got the moments at A, B, and C, and therefore we can now draw the bending moment diagram for the frame. Okay, so we have got this is the frame here. We have joint A. We have joint A, joint B, and joint C. At A, we have 88.34 clockwise. Okay, so at A we have 88.34 clockwise, so we have this, so it's 8.34. Okay, then at B we have clockwise 1667. So we have clockwise 1667. And at B we have anti-clockwise 1667. And finally at C we have clockwise, that's clockwise, okay, 66.69. If you give me the answers into one decimal place, that's fine. Okay, so that would be 16.7, 66.7, and 8.3. Okay.
Regarding this decimal places you're talking about, what I figured out was when you round at the beginning, you don't get the balancing moments at the middle.
That's because of the rounding of errors in the calculator. So it's better to keep your decimal places 2 or whatever, and then you do the rounding off here at the end. Okay, so you do it at the end.
So three decimal places.
You can do 2 or 3 because you've got a calculator. But what I'm saying is that at the final here, when you get the final answers and they are balanced, you can round off to the nearest decimal place. Yeah.
Can you not keep the answer as a fraction?
You can. Yeah, you can. But when you're calculating, you still need numbers when you do the reactions and everything. Yeah, okay. So we have the, don't forget that we have got a point load here of 100 kilonewtons, okay? Do you agree with this now? Yeah? So we've got these signs from the table here, clockwise, positive, anti-clockwise, negative. And you apply it to the beams and to the columns. The rest now is exactly the same as what we did yesterday. In order to find the intermediate value, okay, first of all, let me just sketch the bending moment diagram here. Before I do that, start with joint A. Where is the tension? On the left or right? Where is the tension at A? Is it on the left side or right side?
Right.
Do you agree that the tension is here?
Yeah.
Yep. Tension, you agree there? Tension? Tension. Agreed? Yes? Okay. Because that's important, because that will tell you where, on what side of the member you plot the bending moment diagram. Because otherwise you have your bending moment all over the place, not in the right, not the right shape. Do you agree, everyone, please? Yes? Okay, right. So this is the bending moment diagram here. So we have 8. We have 834 on this side here. We have 1667 on this side here. We have 1667 on that side there. And we have 69 or 66.69 on that side there, okay? And then you have the point load in the middle. So your bending moment diagram will look like this. And it's linear, okay? And that's the bending moment diagram.
Can you explain the bending moment stack?
Which one?
Where you put the values.
Okay, you know the tension is on this side.
Yeah.
So you have 8.33 on this side. Okay, then you've got 1667. Tension is on this side, so you have on this side here 16.67. Okay, and then you have at the top you've got 1667. So you've got 1667 there. At the top here, where you have the tension, you have 66.69. So at the top there, and because you've got a point load here, so the bending moment diagram is linear, and it's going to look like this because of the point load. And on AB there is no loading. There is no loading, just the moments here. So therefore, you join with a straight line. Is that okay? So what we have, we've got this point of counterreflection to determine. Okay? So we need to determine this distance here. So we need to determine the point of counterreflection there. Then we need to determine this point of counterreflection and this one. And we need to determine the maximum moment. Okay? So we need to determine this here. We need to determine this there. And we need to determine the maximum moment. It's okay. So what we do, we take each segment in isolation, and we do what we did yesterday. Yeah. Okay. So take AB, in order to get the, are you familiar with similar triangles? Sorry? Yeah, kind of, not exactly, yeah. Are you familiar with similar triangles? No, okay, let me show you. So let's start with AB, okay? So we're looking at AB. So we start with AB, okay? And this is what we have for AB. And this is the bending moment for AB, okay? One way, if when you have got straight lines like this, you have linear distribution like this. When you have a straight line, it's possible to determine the points of contraflexion here, okay, simply by using geometry. How? You use what we call the similar triangles. If I draw a line here, can you see this line? Yeah. This is A34, isn't it? You agree? What's this here?
16.67.
You agree, everyone?
Yeah.
Focus on this triangle here. Focus on this. Can you see that triangle? Yeah. Similar triangles we have. This triangle here, can you see this triangle? This triangle is similar to this triangle. Okay, I repeat, this triangle here is similar to this triangle because these two lines are parallel. Yes? So you've got similar triangles. This here is similar to this triangle. What does it mean? It means that this side divided by this side is equal to this side divided by this side. So you've got this divided by this is equal to this divided by this. Make sense? Yeah. This is the law of similar triangles. When you have triangles, one is large and one is smaller, but they are similar because the lines are parallel, like here. Okay? So you've got parallel lines. So therefore, we can say that this here divided by this side is equal to this side divided by this. Do we know what's the length of this side or not? No. Okay, let's call it D. Okay, so we have D over. Do we know this side?
16.67.
Good. Do we know the longest side, this one here?
4 meters.
Do we know this side, how long it is?
4 meters.
Exactly, so we know it's 4 meters divided. Do we know this here? Do you agree?
Yeah.
Yes? Yeah, that's it. And that, now I can derive D from here. Can you do for me 4 divided by 16.67 plus 834?
Would you still get 4 marks if you did it another way? So
There is another way. I'm going to explain it in
it's
a
only
minute.
just ratios.
0.16.
Yes, sorry?
0.16.
0.16, yeah. So you have D is 0.16 times 1667. So if you multiply your answer by 1667, please.
2.67.
2 point?
2.67.
Yeah, 2.67. Thank you. And there is another way, yes, of doing it. In this particular case, if you spot, can you see that this is here? This is twice this. Yes. Yeah. This here, this value is twice this value, isn't it? So so in terms of proportionally, this is 2/3 and this is 1/3. Yeah. So you have 2/3 of 4 and 1/3 of 4 meters. And that's because this value is 1/3 of this value. Sorry, it's half of this value. Is that okay? Yeah. So that's another way is to look at the proportions. Was that your?
No.
Okay.
So what I did was add up 16, 6, 7, and 8.34.
Yeah.
Then divide 8.34 by what that is, and then you get the sort of percentage goes up from the bottom, which was 0.
Oh yeah. You're doing the same, but from the bottom.
Yeah.
It's exactly the same. You're still doing similar triangles from the bottom. It's the same. Yeah. Yeah. Now, what I've said now is looking at the proportions of the values here. It gives you the proportion of the length, because this is half of that value. Yeah. Okay. Anyway, I don't care whichever way you want to do it. Okay. As long as you get the correct answer here, use similar triangles. If you're not sure, it gives you the safe answer. Is that okay? So now we know we've got this is 2.67. So you can determine. So what's this length here? If this is 2.67, so what's this here?
So we can't see the
1.3.
1.3. Yeah. To one decimal place, it's 1.3 meters. I mean, here, this is roughly 2.7 meters, okay? Any questions? So whenever you have got a linear distribution, like here, you can always use similar triangles to determine the points of contraflexion. Unfortunately, if you have a parabolic distribution, you have to do the way we did it yesterday by taking an intersection. There is no way around it, okay? But when it's linear, it's easier. Any questions?
Can you put these notes on our these?
Sorry, the notes will be scanned, and I put them onto Aula, with and then you have the recording as well. Okay. Shall we do this here? Member BC. Yeah, member BC, we've got 2 points of contraflexion, and we need to determine also the maximum moment in the middle here. One way of solving BC, you can first determine the maximum moment, this value here. Once you've got the maximum moment, you can use these similar triangles for each half. So you do these similar triangles for this half, and then you do the similar triangle for the other half. So that's one way. Yeah, but you need to find the value of this moment in the middle if you want to do it geometrically. That's one way. Or you can do it by taking sections, cuts, as we did yesterday. So let's do it. So let's do BC now. This is member BC. So we have 16, 67. We have 66, 69. We have, this is B, this is C, and we have the load, the concentrated load of 100 kilonewtons in the middle. obviously we have reactions here. We have reaction at B, which is BC, and we have a reaction at A at C, which is BCB, and the distance we have 2 meters and 2 meters. Can I ask you, please? I'll give you 2 minutes. Okay? Can you work out VBC and VCB, please? Can you try? Have got it with a pencil if you are not sure. Can you work out VBC and VCB for me, please? Take moments about C equals 0. Okay? And take moments about B equals 0. And then you do clockwise moments equals anti-clockwise moments. You can follow the notes from yesterday if you want.
So the BBC equals 0, so equals the left hand side now. So. What about the
Yes.
divided by 4, 62.5. So it's 66.6. Minus 16.6. 250 divided by 4.
All right. That's the force here. Times the net. Yeah, it's the net.
So the VCB equals.
Yes.
Yeah, so it's 16. No, so it's 16. Plus 200 minus 66. You take away this one. Equals.
Well, because you take out about B.
Yeah, that's exactly.
Yeah. Okay. So have you got answers? Has anyone got answers? Did they add up to 100? Excellent. Yeah, well done.
So you know you can check just that plus that equals. Yeah, we done it.
Oh, good. Okay. Excellent. Well done. Yeah. Very good. Well done. Right, let's do it. Do you want a break? We do this and you want a break?
No,
Sorry? It's up to you. We can have a short break. Okay, let's do the reactions first. So we take moments about, let's start with moments about, I don't know, C, okay? So clockwise equals anti-clockwise about C. Clockwise we have 66.69, that's clockwise. And then we have the reaction VBC times the length for that's clockwise equals anti-clockwise. We have about C, and this is anti-clockwise, so we have 16.67. And that's it. Yeah, we take moments about C. Okay.
Will you take into account the weight?
Let me start again. So we take moments about C. So we have about C, we have clockwise. Yeah. Then we have BBC times 4, that's clockwise. Then anti-clockwise we have 66, and then we have the 100 here, which is 100 times the distance 2. Is that okay? Yep. So therefore you can get the VBC from here. Please use your calculator. So we have 1667 plus 200 minus 66.69, and you divide by 4. What do you get? What do you get for that, please?
62.505.
62.505.
505.
Let's say 51 kilonewtons. And then we do the same. Take moments about B now. So moments about B. About B we have clockwise 66.69. Clockwise we have 100 times 2. And then anti-clockwise about B, we have VCB times 4 and 16.67. And then that will give you VCB. Okay? Should be 37-ish. 37.49. 49. Thank you. If you want to have it as a one decimal place, it's up to you. That's 62.5, and that's 37.5. It's okay. Yeah. So now we can determine the moments. Let's call this point here D. Okay, so we call the point here in the middle, D. Then the moment at D. What is the bending moment at D? Okay, let's have about 10 minutes break. Is that okay? Yeah? And then we finish this exam.
What happens if it's this one and that
Well, I left my phone.
Absolutely.
That's mine, mine is the opposite way around. You know how it works? Let's hope that's one. That's like I put it, do it with that, comes with that one. Because of that one, not that one.
Is your towel yours? Towel?
No. You've got to rearrange it, all this is the same. That one comes this time, comes in mine. That's in mine. That's what I'm saying, see, when I turn back to the calculator, these are the opposite way around. So even though I'm calculating that formula, it's for that answer.
Week 2.
I'm not going to take that's right, I totally get that.
Just must be minus 66 somewhere. So you must minus that from that, no?
Usually they're fine.
I know, we didn't really explain that.
No, I'm not going to do that. I'm going to get back later.
Then the cost of X can't be 4.39 because the beam's only 4 metres. I know it's not what I'm sorry.
Well, what is it?
Brain's blank, you can zone out.
We do that different ways, right? But we need to go home. It's like 2 hours only, so we don't even need it.
That's why we sort of 17 days.
Has anyone got any structured notes, like step-by-step notes for structural design?
We not making them.
I made like for like one first 4 lessons or something, which no question came up.
Now's your time to start making.
Yeah. In his plan, start. Honestly. That really is on like about 10 minutes worth. I literally have like half 10 minutes plan well.
I've got all the notes in the bag in the hotel. I just got to go through.
I think every single note I made, like, just waste. I think you love it. I literally need to go through like 10 different questions and literally write step by step what you need to do, just the steps. And then I'm sorry.
It's never as easy as that. It's like you need to actually understand it, that's the thing. Because I always think, oh, just walk down every marriage and parents know what I'm doing. But second, like, sloppy third off, never know what to do. You need to understand.
Yeah, it's actually
The question is follows on, so if you make one mistake, then you're kind of that's the problem. It's just better to have 10 questions than 12. This guy's quite good. You actually want to do everything in steps.
Yeah, and that was all recorded.
Yeah. I like to do how's work going, mate? How's work going?
Oh,
Work.
it's alright, we're good.
You guys in the same section, are you?
No. Different section.
What about Amrit? Is it? What is it?
Where is it? I don't know. It's not for you, I don't know.
He said, how long? Okay.
I'm just running on to
Yeah.
I've got to the progressive point.
Yes.
Obviously, I've put that into the calculator and I'm like giving it to one tutorial. Obviously, I know it's can't work, it's too big. Where am I going? I'm following. I haven't put it in check of that. But that check. It's too easy to design.
That's actually the 14 settings. Not one. C is 14, minus 14 plus 7, isn't it? I don't know where you get minus 1 from. So that's your A, that's your B, and that's your C.
Yeah.
Yeah. That's
But
probably
then it's the same issue with this one as well.
That's called grip.
what's wrong with B?
Because you know, the beam's only 3 meters long. Because you don't know.
Yeah.
I think it's sure it's called.
So you obviously made mistakes on one back. Probably made a mistake.
But no, I've got the actual tutorial here. This is what's in the tutorial.
So the choice is either simple. Not 6 pieces, minus 6 pieces. Minus. That's fine.
Okay. Okay, I think we're going to start, please, because it's still recording. So MD. Okay. So MD here, you can calculate MD from the left side of the right side. It doesn't matter. Okay. You get exactly the same answer. You can try it. So if you take, if you calculate the moment at D from the left side here, what is the bending moment at D? It will be this reaction times 2. Yes? So it will be 62.5 times 2. And then you've got this here 16.7. So minus 16.67 or 7, okay? What does it give, please?
So where did you get the 62 from?
It's the moment about C, isn't it?
It's, yeah, we want the moment D here, the moment at D, so it will be 16.7 or 67 times 2, VBC, which is 52.5. Okay, so the moment at D, 62.5, that's the reaction here. Okay, this reaction is 37.5. Okay, so the moment at D will be 62.5 times 2 minus 16.7. Is that clear? Yeah? So this is by taking the moments about D from the left. So, and that gives...
108.3.
Sorry?
108.3.
108.3. Thank you very much. Kilonewtons meters. Can you quickly calculate MD from the right side? See if you get the same answer. Can you calculate MD from the right side? Okay. See if you get the same answer. So try that. So if you do it from the right side, it will be 37.5 times 2 and then minus 66.7.
Minus plus.
That one is 37, if you, the moment at D would be 37.5 times 2 minus 66.7. And hopefully you should get 108.
Doesn't add up, right?
It doesn't give you that. A.
No, it's nothing to do with clockwise or anti-clockwise. What did I say yesterday when you take, when you determine the moment at the cut, which convention you use?
Oh, just minus.
Yes. So 66.7 give you a sad face, isn't it? Yeah? And the VCB gives you a smile. That's right. Yeah.
The BCB is back up, so it's do that.
VCB is going up. And the 69 is negative. Yes,
7.5.
yeah. Okay.
By 2. Yeah.
So what do you get? What answer do you get?
You get
From the right.
8.3, but that should be negative, shouldn't it?
108? You get 108.3 as well.
No, you get 8.3, but that should be a negative figure. In
No,
order
you
to get
can't get
the
8.3.
We've got 8.3.
that should be a negative figure.
He meant to put plus the 100 on. Okay.
If you take it from the right, it's 37.5, yeah, times 2, minus 66.69.
It gives me 8.3.
And from the right, 62.5 times 2, minus 16.7.
Why do they cut through the section?
So one of the answers should be negative in order to get the.
Wait, I'm just looking at, wait a minute. Did we get any,
You know, on that
Opposite way round.
step before, when he got.
That's what I thought.
37.5.
That's what I put it as.
What was your? Oh, you did.
Shouldn't VCB and VCB be the other way around?
I'm just checking the answer just for a moment, okay? So, moment about C, 1 minute. Yeah, I'm just checking the reactions, okay? So, moments about C, we have B, B, C. Okay. Times 4, yep. And we have C, C, yep. That's clockwise. Can you check this answer for me, please?
I think that's what you
Can
talked
you check
about.
from the calculator?
To change the values for
I'm checking that because I relied on someone shouting the answers for me. And obviously, no. This is 37.5.
Oh,
Who shouted the answers for me? Okay, 37.5. And then I guess the other one will be 67. So I'm going to check it.
Still the same answer.
that's why we just did it. You know the forms we had before?
And that's 62.
That doesn't really matter, to be honest.
Does it matter?
Because
Does it
the
matter?
answer for 100,
The forms
regardless.
before.
Exactly, yeah.
So
Okay.
those numbers being around. that's not-
One moment, slowly. I mean, the good thing is that you can always check your answers. That's what I said yesterday, isn't it? So I know that moment at D should be the same from left or right, okay? If I find that's not the case, I go back one step and check my answers. Very important, okay? So now, the moment at D now from the left will be, that is 37 now, okay? That's 37.5, and that's 62.5. And I must get the same answers, otherwise we are stuck here. So, from the left we have 37. Okay, so MD, from the left we have 37.5 times 2 minus 16.67. If I want to leave it as two decimal places. Or I should have the same answer from the right here, which is 62.5 times 2 minus 66.69. Please give me the same answers.
It is.
Yes. Yeah. It's not a problem making mistakes, as long as you know. And then you can rectify. Yes. Yeah, I mean, when you get your answers at the end, you can. No, you can round off to one decimal place if you want. That's okay. Yeah.
58.3. Or 3.3. Yeah.
That's fine. Then you can round off. Yep. Yeah. You will never get exactly. You won't get exactly the same answers because your calculator and what you write down will be rounded off. So that's okay. So what's the answer? 8 point, did you say?
58.3.
58.3. Thank you very much. Okay?
That's why you should check it.
Yeah, this is from the left and this is from the right. Okay. So, so we've got now the moment at D, which is this moment here. Okay, this is 58.3. All right. So now we need to determine these 2 points of contraflexion, the position. I can use similar triangles for the left shape, and then I can do the same, use the similar triangles for the right shape. That's one way of doing it, because you know everything. You know this value here. Okay, you know this value, you know the length, so you do what we did here in exactly the same way. Is that okay? So you can use similar triangles. So the key was to find this value first. Now we can use similar triangles. Or it's if you want, you can take a cut between B and D, and then take a cut between D and C. You get exactly the same answers. Okay? There are always, in analysis, there are always different ways of checking the same answer. Okay? Always. Shall we do similar triangles?
Yeah.
Okay, let's do similar triangles. Let's do similar triangles. So this is the diagram I have. Sorry, I have this here. It's not to scale, okay? We have 66. I'm going to round off, okay? 66.7, 16.7, and 58.3. So I'm going to call, this is B, this is C, and let's recall this point D, yeah, as we did before. So this is point D. Okay. Let's call this distance here D1. And let's call this distance D2. So I'm going to, the first one is this here. Okay, so basically we're looking at this triangle. Can you see this triangle here? Can you see the big triangle? Can you see this big triangle here? So we're looking at this big triangle and this one. So using similar triangles, this triangle and this one. Okay, which I have got here. Is that okay? Yeah. So we have got this, which is 16 point.
You can't see it.
Oh, sorry, I do apologize. So we have this big, the small triangle, this one, and this big triangle, this one here. These are the two similar triangles, okay? This one and this one. Is that okay? So we have 16.7 divided by this length, which is D1, equals to this length, which is 16.7 plus 58.3, and divided by this length, which is it 2 meters? Yeah, 2. So therefore, D1 will be 2 times 16.7 divided by 16.7 plus 58.3. And you give me D1, please.
.445.
0.445.
0.45.
So 45, yeah. So that's so from. Thank you. Does it make sense? Yes, it does. Yes, it does. Because the length is 2 meters here, and this is roughly a bit less than half. So that's okay. Now we can look at the similar triangle for this one here, for this. Okay. So we're looking at the big triangle, this one here, and this small triangle there. So this length is 2 meters, isn't it?
Yeah.
Yeah. So. So what we have, please concentrate. We have this triangle here and this triangle there. Okay. So we have this, which is 66.7 divided by this length, which we don't know is D2, equals to this here, okay, which is 66.7 plus 58.3 divided by this length, which is 2. So therefore D2 will be 2 times 66.7 divided by 66.7 plus 58.3, and you give me the answer, please.
1.07.
1.07, thank you. 1.07 meters, and that's from C, from there. Yeah. And these are the lines as well, isn't it? Was it because of the corona? It's okay. Yeah, so this is the 1.07 here. And this is the 0.45, okay? Right? So now we've got a fully annotated bending moment diagram for the frame. Everything, okay? With intermediate values with the points of contact flexure all defined. Okay? As you could see, we didn't really do anything new. Okay, we used exactly the same knowledge that we acquired yesterday for continuous beam to solve a frame. Okay. Is that okay? Yep. Any questions? No?
We're going to do the one that's got three, like it looks like a T, like the beam. Like this one here, I don't know how to.
The one uploaded onto Moodle.
No.
Into Aula.
Yeah. Looks like that.
We could do.
Oh, only if it's an exam, not.
I don't know what's in the exam. I think there's another one where I uploaded the video of it, isn't it?
This is for the full-time students. So this is just looking at that one.
Yeah. No, what I'm saying is that for your case, I think I've uploaded a different one, if I remember. I've got a lot of examples, so I don't know which ones.
Okay. Oh, it's not that.
Yeah, look under your own.
Kier. First one. There you go. Second lesson. Is it here?
Okay, that's a 3-span, which is what I need. So I need this. Can you look at scope? Any more? Then I can. Okay. All right, that's fine.
Yeah, this is for Thursday.
Oh, we've done the Thursday one today.
Yeah, this Thursday.
Good.
Tuesday we have.
It's because I skipped the 3-span, that's why.
Oh, we're going to do the thing.
Frame.
Oh,
Yeah, frame. Okay, what I would like to do is something different. Okay, we've got about 20 minutes. So let's do example number 2. I'd like to give you things that will help you with the exam. So that's what I'm trying to do.
You are answers, it's not. I don't use this for
Okay? Is that right? So what we have here, we have a frame, at A is pinned, so we have a pin at A. In other words, there is no moment at A. And then we have got at C, it's fixed. We have a concentrated load on the column, AB, in the middle. So it's 2 meters, 2 meters. And we have a uniformly distributed load on BC of 1.5 EI, okay? I don't think we are going to finish this today, so we're going to finish it tomorrow. Yeah, we have tomorrow and Thursday, isn't it?
Thursday and Friday.
No, with me. I know you've got till Friday, but I think with me you've got tomorrow.
No.
We don't have any.
No, not tomorrow. I've got the other group. I've got you Thursday.
Yeah.
I've got you Thursday, sorry, yes.
What time and where are we? Because I think our timetables are different. So we could do now before.
I will announce it. I think Thursday it's 9 a.m. I think. Yeah.
If you put like your timetable on the.
I will announce. I will put an announcement for the time and the.
Ours says 10 o'clock.
Sorry.
Ours says 10 o'clock on Thursday.
I will check. Yeah, I will check and I will.
Oh, we're not showing the labs on Thursday, are we?
You have got labs, but I don't know where or when or whatever. Please, don't ask me. Sorry.
I think that's next week.
I think you have got labs next week, isn't it? Yeah. I think Pam did put the timetable for the labs, isn't it, on our lab? In the announcement community, no? No? I'll ask her. Because you need to know your group as well. Okay, let's make a start. Let's make a start. Shall we do the fixed moment? Yeah, I mean, as earlier, this is like having this field, basically. Look. You see that? Yeah, this is like having a continuous beam like this. So you can look at it in your head. You can think of it as if you had something like this. Okay. Obviously, it's a frame. It's different, but what I'm saying is that this is like an equivalent arrangement. So first of all, let's do number 80. So this is 80. We have got we've got this for number 80. And the load is in the middle. So what's the fixed end moment, please? What is it at A? If it's single supported, what is it at A?
0.
0. What is it at B, please? Look at your table. You need your table here.
0.
It's not 0 because at B it's fixed. So look at your table. But it's the same, isn't it? But
The opposite way around.
the opposite way around. So what you can do, you can be clever and look at it like this. Okay. You don't have to, but what I'm saying, it's just like so basically this is negative this one, yeah, like this. So if you turn it around, can you see this? This is going to be exactly, yeah. Isn't it? Yeah. Yeah. Just be careful with the sign because it's the other way around.
It's the opposite.
Yeah. The bending moment becomes a clockwise, becomes positive. Yeah.
Yeah.
Everyone else. Okay. So we have a plus. What was it? 3W L over 16. Is it 3WL over 16? Yeah. So we have 3WL over 16. So it's plus 3 times 20 times 4 over 16. Because it's, where is the table? I lost my table. Where is my table?
Yeah, okay.
You get it why it's plus?
Yeah.
Yeah. Everyone else, do you get it why it's plus? Yeah. Because basically you flip it horizontally. Okay. So what's the answer, please?
15.
15. Thank you very much. So we have 15 kilonewton meters. Yeah. And then we do this, and then we do for BC. This is BC. And we have UDN. Okay. W is 5. Okay. And the length is 3 meters. What is the fixed moment at B, please? Is it minus W square over 12?
Yeah.
Yeah, so it's minus WS squared over 12, which is minus 5 times 3 squared over 12. So 45 divided by 12, 3 points-ish, isn't it?
Minus 3.75.
3.75, thank you very much. So minus 3.75 kilonewton meters. I will leave 2 decimal places at this stage, yeah? Until I've done my table, and I've got the final moments in my distribution table, then I can start rounding off, yeah? So leave your decimal places at the earliest stages, please, okay? So FE and BC, CB, sorry, will be exactly the same with the plus, because we have symmetry. Okay, just remember that this is, now we do the distribution factors and we are done, okay? So DF's distribution factors. So we've done the fixed moments, okay? Now we do the distribution factors. So we have got 3 joints. We have joint A, we have joint B, and we have joint C. Joint A, we have 1 member, and that's DFAB. What can we say about the distribution factor for A? 0, yeah, exactly. Is it 0 or 1? Is it 0 or 1?
1.
Yeah, because it's pinned. If it's fixed, it's 1. If it's pinned, it's 0. Okay? And then we have DFBA, which will be, now this is where you need to be careful. Yeah? Do you remember what I said yesterday? If one end is pinned,
0.
like here. Exactly. So your flexion rigidity here, you need to multiply it by 0.75 because you have a reduced rigidity. Okay, so we have 0. That's the stiffness of BA, so 0.75 2 EI, 2 over, 2 over, what's the length? 4. Yeah, divided by 0.75, 2 over 4 plus 1.5 over 3. Yeah, you can forget about the EI because it will cancel. Yeah, so you take the 2 EI over 4, 1.5 EI over 3, 2 EI over 4. Obviously, the EI will cancel, so you just ignore it. If you can work this out for me, please. 0.75. I don't know. You just work it out. I made up this example completely now. Okay, completely made up.
What was 0.43?
0.43. 43. Thank you. And then for BC, okay, we have stiffness of BC, which is 1.5 over 3, divided by 0.75, 2 over 3, and 1.5 over 3. And hopefully that should give us 0.57, I hope. No, 0.57? Thank you. Okay, And you can see that the sum is 1, yeah? So that's okay. And finally, for joint B, we have only one member for joint C, sorry, and that's CB, and it's going to be equal to 0. Okay, here A is pinned, okay, and here C is fixed. Can I just do the table? Because it's 42, so we have about 4 minutes, 5 minutes. Is that okay? Yeah, I do the reason I want to do the table, because then I can start from the bending bone diagram and do the intermediate values. Okay? It would be easier. I don't want to, stop in the middle here. Any questions on the fixed moment distribution factors, please? Anything at all? Okay. The table should be straightforward. Okay. So let's do the moment distribution table. So moment distribution table. So we do the moment distribution table now. So distribution factors we have at A we have 1, 0.543, 0.57, and we have 0. Fixed moments we have at A we have 0 because it's bent. Then we have plus 15. Then we have minus 3.75 and plus 3.75. So we have an out of balance here. 15. Can you do for me 15 minus 3.7? 11.25. Thank you very much. So it's plus 11.25. So the balancing would be the opposite of that. Yeah. So the balancing would be the opposite. In other words, I'm going to multiply minus 11.25. Can you do for me 11.25 times 0.43? Sorry? 4.84. 4.84. Thank you very much. And 11.25 times 0.57.
2.76.
2.76. That can't be right.
No, 6.41.
Sorry?
6.41.
41. Yeah, that makes sense. Because now when you add these two, you should get 11 minus 11.25. Thank you. Yeah, and now see that this is the balancing. Balance. Okay, and now we carry over. Okay. So do we carry over from B to A?
No.
No, because. Yeah, this is why you need to be careful. Yeah, because A and A is pinned, so there is no carryover from B to A. Is that clear? It's only if it's fixed. So we carry over from B to C, but we do not carry over from B to A. So there is no carryover this way, but there is a carryover from this side. So what is 641 divided by 2, please? 3.20.
3.20.
2.0.
3.21.
Okay, let's do 2-1. Yeah, thank you very much. Now we can draw a line. We have 375 minus 321. It's 0.54. It's a very small moment. And we have 15 minus 484. 6, 11, 10. Is it 10, 16?
Yeah. Oh, which one? That one.
So we have plus 10, 16 and minus 10, 16. And obviously here we have 0. And these are the final moments. Okay? These are the final moments. And you can see that the moments now are balanced. Okay, spot on. We finished exactly 11:48. Okay, so next week on Thursday, we're going to finish this example here, and I will run over some tips and so on for your exam and so on. Is that okay? Yeah. Thank you very much. So I'm going to stop the recording.
I don't know, I must have to do time.